First started creating screencasts back in 2020 when COVID hit, and that was the way to deliver our curriculum. And I never thought that years later I'd still be creating screencasts, and years later I'd get COVID for a second time. So if you hear a little bit of coughing or sniffling, it's because I've just gotten over another bout. This chapter, as you can see by the title, is about thermodynamics. And of course, thermo you recognize as being heat, and dynamics, coming from the Greek word for power, tells us that this chapter is going to be not just a description of heat, which you've already learned something about in the previous chapters, but how heat does work, or how work can create heat, and tells us some very important things about the nature of energy itself, and that the fact that nature ends up as energy ends up as low temperature heat. So we're going to learn about the first law of thermodynamics in this chapter. In a later screencast, we'll talk more about the second law of thermodynamics, which has to do with entropy. But there is also a zeroth law and a third law of thermodynamics. Now, you might say, why would we have a zero law of thermodynamics? And the reason is, back in about 1930, when this law was first articulated by a guy named Ralph Fowler, the other laws, first, second, and third, were already well in place, and they weren't going to change the numbering. And it's sort of like these three laws, in a sense, sort of assume this zeroth law. And the zeroth law basically says that if you have two thermodynamic systems that are in thermal equilibrium with a third system, then those two systems are in thermal equilibrium with each other. It's kind of like the transitive property of equality. If A equals B and B equals C, then A must equal C. Another way of thinking about it is when thermodynamic systems are in thermal contact, heat will always flow, the net heat will flow from warm to cold until the temperatures are the same. So it stands to reason that these different systems, if they're in thermal contact, will reach thermal equilibrium, which would mean a constant temperature. Now, the third law of thermodynamics, which I don't believe the chapter mentions, has to do with the fact that as you approach absolute zero, your entropy reaches a maximum, where entropy is a measure of the disorder, and your temperature, as it approaches absolute zero, would be the lowest theoretical temperature you can have, at which point you no longer have any type of translational, rotational, vibrational kinds of energy, but more of a quantum vibration, if you can call it that. That's where the quantum effects come in. And so that would be as you approach 0 Kelvin. And we've actually, in our research experiments, actually have reached, I think, less than a millionth of a degree Kelvin. But of course, when you get down there, anytime you try to extract heat from something that is that cold, you typically need to put it in some place that is colder in order to make your first system colder. Well, as you approach absolute zero, there is no other place to dump your heat. So with that as a background, let's get into this chapter. The chapter is challenging on the theoretical level, not on the math level, though some of the math problems look a little weird. And the biggest challenge here is going to be keeping track of positive and negative signs for energy and for work. And we'll be referring to chemistry and how we handled signs in chemistry a little bit later. So finally, we're going to talk a lot about heat engines. And of course, your internal combustion engine of your automobile. Not talking about an electrical vehicle now. They're becoming so common that I have to differentiate between internal combustion engines and electrical vehicles. But the internal combustion engine, of course, is where combustion takes place inside this engine, and it actually produces an awful lot of heat in the form of a rapidly expanding gas, which pushes a cylinder, a piston out of a cylinder, and that can be connected to various mechanical devices that eventually make the wheels go round. We'll talk more about that in a later screencast. So let's talk about work. You remember, of course, that work equals force times distance. And we're not going to have to worry about a cosine theta in there because we're going to be talking primarily about gases in this particular chapter. Your human body is an engine. And just a little bit of philosophy here. You want to be careful never to say that the human body is just an engine or the brain is just a computer. As soon as you make comments like that, you are in a sense reducing the brain to a computer when the brain is so much more than that. And you're reducing the body to a heat engine when the body is so much more than that. This is part of the philosophy of reductionism. And if you take reductionism to its extreme, which a lot of people do, and that is you keep reducing, let's say, the human body down to a bunch of organs, and the organs down to a bunch of tissues, and the tissues down to a bunch of cells, and the cells down to a bunch of cell components, like the different parts of a cell, the nucleus and the ribosomes and the Golgi apparatus and the endoplasmic reticulum and the cell membranes. And then you reduce those things down even farther to eventually you get to proteins and carbohydrates and molecules like that. Then you reduce that down to atoms, and you reduce the atoms, if you can, down to protons, neutrons, and electrons. And at some point, you're going to say we've reduced it as far as we can go, and that's all the human body is, which would be totally false philosophically and theologically. For example, think about a house. If you take a house apart, you have reduced it down to its nails and two-by-fours and pipes and electrical conduit and mortar and insulation and things like that. But what you've also peeled away as you take the house apart is all of the information, all of the design and creativity that the craftsman put into the house in the first place. So just because a house can be reduced to a bunch of its component parts does not mean that that's all a house is. In fact, you could say that most of a house is not the stuff that it's made out of, but is the design and the craftsmanship and the artistry of the workers that conceived of the house and assembled the materials and put the materials together and made it as functional and as attractive as a house can be. So as Christians, we would definitely oppose this philosophy of reductionism. But of course, once you reject the ultimate designer and artist himself, God, you have no recourse but to assume that everything can be reduced to just a bunch of nuts and bolts, and that's all we are. It's a pretty depressing kind of philosophy. All right, back on track. Energy can be transferred to a system by heat and by work. And we're going to be looking at the interaction between these two quantities a lot. And we're going to be primarily focusing on gases because gases, when you do work on a gas, you can cause that gas to occupy smaller and smaller amount of space. Or an expanding gas can do work on its surroundings. And not so much with liquids and solids. So we're going to be focusing our attention pretty much on systems of gas as we study these principles of thermodynamics. Now, you also remember that pressure is defined as force per unit area. So force equals pressure times area. So instead of force, I can put pressure times area into my equation. You can see also this negative sign. And the negative sign is important to keep track of because just like with, if you remember, F equals negative kx, Hooke's law, this negative sign there is reminding you that when you pull on a spring, the spring is trying to pull back. And so the negative sign is sort of the equal and opposite. And these negative signs are going to be very important because it's going to give us a sense of directionality. When we talk about the relationship between our system, whatever it is we're investigating, let's say a bicycle pump that we're compressing air with, or the cylinder and piston of an internal combustion engine, we have our system, but everything outside the system can be called the surroundings. Or this book will also use the word environment. In chemistry, we primarily use the word surroundings. So energy can go from the system to the surroundings, and it can also go from the surroundings into the system. But the same thing is going to be true of work. If I do work in blue, the system can do work on the surroundings, and the surroundings can do work on the system. And so the directionality of the arrow is going to be represented by the negative sign or the lack of the negative sign. And this is what we have to keep track of. You might remember, of course, in chemistry that we have exothermic. And exothermic is when heat is exiting the system, and we give that a negative symbol. And we have endothermic, and that's when heat is entering the system, and that's a positive sign. So when we talk about work, we're going to use the same type of numbering system. When the surroundings are doing work on the system, that's going to be positive. And when the system is doing work on the surroundings, that's going to be negative. It wasn't always that way, this consistency. This was changed, I don't know, sometime early on in my teaching career. They decided to be consistent between chemistry and physics, because when I first started teaching, there was no consistency here at all. So this is how we get back up to here. This is how we get this equation. Work equals negative pressure times the cross-sectional area times the degree to which you compress the gas. Your delta Y is how much the distance by which the gas has been compressed inside a cylinder. And the main equation then that you want to focus on then is this. Work is going to be defined as negative pressure times my change in volume. Change in volume, because area times my length is equal to the volume. And here you have a bicycle pump. It may not look like one. We could put a handle up here, which you can push down on. The gas is pictured here in red. This part of the container, which is open in the front so you can see what's inside, is the cylinder. And this part right here is the piston that, when it's moving downward, is compressing the gas. When it's moving upward, it's allowing the gas to expand. Or it's being expanded, it's moving upward because the gas is expanding. So the analogy here, way back when we were first introduced to the concept of work being force times distance, as long as the force being exerted is in the same direction as the distance. Here's my change in x. moving this box with a certain velocity v. We don't need the cosine theta, so work equals force times distance. And I'm going to try to be consistent with my nomenclature here. And then when we look at this picture here, we have the same worker pushing on the back end of a piston and exerting a forward force on that piston, which is compressing the gas that's inside this very, very large cylinder and compressing it by some distance x. And of course, it has a certain cross-sectional area here. And so the work that's going to be done, as you might recall from the previous equation, which I just looked at, is going to be the pressure times my, this is what I'm referring to down here, pressure times the change in volume. So we can talk about work being done on a gas. And so the work is coming from outside the system. And in the picture, it's by the guy pushing on the piston. And it's compressing the gas, doing work on it, confining it to a smaller space, which means you're going to get more collisions of gas molecules inside the cylinder, probably raise the temperature while you raise the pressure. And you can also have work done by a gas. If the worker backs away from the piston in the cylinder, that compressed gas might begin to expand and push the piston back out again. And so that's work being done by the gas on the piston, which would be part of the surroundings or the environment. So we use work, this book uses work with the little ENV for environment, doing work by the environment or doing work on the environment. So when work is done on a gas, as defined in the equation above, the internal energy of the gas increases. So what do we mean by internal energy? The internal energy, often represented by the letter U, represents the energy that is contained by all the molecules and the atoms of the material. Ions if it's a solid crystal, but we're talking here about gases. So about the molecules and atoms, it's the energy that these molecules and atoms have, which can be rotational, vibrational, and translational. So let's move on. Apply the definition of work at a constant pressure. I'm reading right here. And we have a system, such as the picture that we just looked at. We have this much pressure, and you should recognize this as being air pressure, sometimes represented as P sub O, and P being pressure, and the PA being pascals, and 1.01 times 10 to the 5th pascals equals 1 atmosphere, which is the standard pressure on the surface of the earth at sea level. And as our weather changes, for example, sometimes we dip a little bit below 1 atmosphere and have a low pressure, cloudy skies, good chance of rain or snow depending on the temperature, or high pressure, clear skies, a lot of sunshine. And it's just a matter of plugging our numbers in, as most of the problems in this chapter are. Now, keep in mind that if we want our answer to be in joules, we're going to have all of our dimensions, be they lengths, areas, or volumes, in terms of meters. So make sure you can do those conversions correctly. And a Pascal, of course, is a Newton per meter squared. Now, another thing you're going to see an awful lot of are PV diagrams in this chapter. Pressure volume diagrams. And here's your first one. Pressure will be on the y-axis and volume will be on the x-axis. And you'll notice that you'll have a starting point. In this case, we're starting on the right where the letter I stands for the initial, and we're going to end up here at the final. And you'll notice that when we go from initial to final, that requires in this diagram to draw an arrow going to the left. And you'll notice that the pressure does not change in this diagram. The pressure is always whatever that number is on the y-axis, but your volume is changing. The volume is changing down here. And then the area under here, and in this particular diagram, you just find the area of this rectangle, which might even be a square. The area would be pressure times change in volume, which is work. So the area under the PV diagram is the work that is being done as you go from the initial to the final state. Now, in other diagrams, it's going to require you would have to use the methods of calculus to find the work being done, or you'd have to estimate it by creating boxes, as you will see. Now, there's a bunch of vocabulary words in this chapter, and we're going to come across them methodically, but the first one is an isobaric process. And iso, you recognize the prefix as meaning the same, like an isotope, or an isosceles triangle, or an isomer in chemistry. Isobaric, baric is another word for pressure. One of the units of pressure is the bar, B-A-R. So isobaric would be a process where the pressure does not change. And this picture here is an isobaric process because the pressure does not change, and yet somehow the volume is going from a large volume way out here, and it's ending up in a much smaller volume as something is doing work on this gas, changing its volume smaller and smaller. And this would be an isobaric process, a process that does work at a constant pressure. We talked about this path, I'm now redrawing it in red, from initial to final. That, we call that a path, the path taken between the initial and the final states. The area under the graph is the work, we already mentioned that. We have to keep track of our signs. If the arrow on the graph points towards larger volumes, the work done on the gas is negative. If the arrow on the graph points towards smaller volumes, then the work done on the gas is positive. So if you think about it, if the environment, if the surroundings are doing work on the gas, causing it to occupy a smaller volume, it's coming from the outside in. And that, by definition, is assigned a positive symbol. The opposite of that would be negative. So, look at this quick quiz. We don't normally do these, but this is worth investigating. We're going to be looking at several PV diagrams, and we're going to try to organize those from the most negative work being done, negative, to the most positive work being done. And if we look up here, here's our 4 diagrams, and you can see that in diagram number 1, we're going from my initial state, which is a pressure of 1 atmosphere, 10 to the 5th pascals, and 1 meter cubed, 1 volume. That's our volume, is 1 meter cubed. And we're going to end up with a pressure of 3 atmospheres and a volume of 3 meter cubed. So left to right, we're going from initial to final. Over here, initial to final is going from left to right. And the 2 graphs, letters B and D, we're actually going from right down to left. Right down to left. So right off the bat, we can say that graph A and graph C are negative, because you can see that something is doing work on, that my system is doing work, and as a result, the volume is getting greater and the pressure is getting greater. And the same is true in picture C. In graphs B and graph D, you can see that something from the outside must be compressing my gas, making it go from 3 atmospheres down to 1, from 3 atmospheres down to 1. So it's coming from the outside, so that's a positive symbol. So now we know which ones are negative and which ones are positive. Now, which ones are the biggest and which are the smallest? And for this, we simply find the area under the graph. And because these are pretty geometrical, we can add up this triangle and this rectangle. We can add up this rectangle and, let's see, this rectangle and this triangle. And then over here and over here, we can add up those areas. And when you add up the total amount of area, you see that the sequence from most negative to most positive goes from A is most negative, C is not quite as negative, then B is positive, and D is the most positive with the most area underneath the line, underneath the pathway. And in example 12.2, we're supposed to look at these first two PV diagrams, PV graphs, and find the work done on the gas in picture A, graph A, and then find the work done in picture B. Of course, one is negative, as we already said, and one is positive. And it's pretty straightforward math. In order to find the total area under the graph, which is the work, we have to add up the area of our two geometrical figures. No problem. Down here, add up the area of the two geometrical figures for PV diagram B, and to get the total work being done. And one thing you should notice that in both cases, the paths in the PV diagram start and end at the same point. In other words, in these two diagrams, both start at 1 atmosphere, 1 meter cubed. Both end at 3 atmospheres and 3 meters cubed. But the pathway is different and the directionality is different for both. So they represent two different processes. And one is the inverse or the negative of the other. I already mentioned that 0th law of thermodynamics for you that presumes the first law. Now you might remember the first law. You've had this before in many contexts as you go through science. And the idea is energy is neither created nor destroyed. Energy just changes forms from one form to another form. Or if you think about all the different ways we've talked about conservation of energy. Well, this is going to be a deeper dive into what the first law is. Now, point number 1, more philosophy here. We say that the first law is universally valid. Now, the farthest away any human being has ever gone is to the far side of the moon in orbit, to the dark side. We've sent devices beyond that, but and here we are calling this a universally valid law, just like we called the law of gravity, the universal law of gravity. And so whether scientists want to admit it or not, they are presuming that there are universal laws. And even though we only have been in a very, very small corner of that universe. And these universal laws then must describe patterns and regularities that are true everywhere in the universe and every time in the universe. And Scientists believe this. They take this on faith. And there's good reason to take this on faith, certainly from an experimental point of view. When we do experiments on Earth and extrapolate it into the universe, or when we look at it mathematically, the language of the universe, but certainly theologically, or think of it in terms of the Christian doctrine, if there is a sovereign God who, according to Scripture, like Hebrews 1 and Colossians 1, sustains his universe, is a covenant-making, covenant-keeping God who makes sure that his covenant promises that he makes not just with people, but also with plants and animals and the fixed laws of the universe, for those to be sustained from day to day, in order for us to do science and to make predictions and to make assumptions and build on those assumptions, this follows from what the Bible says and what creation reveals about the character of the Creator. Creation reflects the Creator. And so there's a solid foundation for believing that these principles, when we get them right, are universally valid. So there's a little bit of a philosophy diversion. So, moving right along, there are two ways that energy can be transferred. One of the ways that we transfer energy from one place to another is by doing work on it. And again, we're going to be using the word the system and the surroundings, or the system and the environment. Chemistry usually talks about surroundings. This physics book is talking about the surrounding environment or just the environment. The other way, of course, is by energy going from one place to the other in the form of heat. And we talked about conduction and convection and radiation as ways in which heat can go from one place to another. Now, there's a lot of stuff I've highlighted in yellow here that we're going to read through. This is all kind of theoretical, but it's foundational. Other processes for transferring energy into a system. So if we're talking about moving into a system, this is going to be in the positive direction, coming from the environment. Any work done through the expansion or compression of the system results in a change in the internal energy. A change in the internal energy of the system. And that internal energy means the system, we're thinking primarily of gases, are made up of atoms and molecules. Atoms, for example, of gases like helium, argon, neon, krypton, xenon, radon, or molecules of gas like the Brinkelhoff gases, hydrogen and nitrogen and oxygen and fluorine and things like that. And of course, more complicated gases as well, like carbon dioxide and water vapor. But a change in internal energy results in measurable changes in the macroscopic variables. These macroscopic variables would be the variables that are very easy to measure, very straightforward to measure, which are pressure, temperature, and volume. And we're going to be talking about these three quantities all the time. You might remember PV equals NERT. There's my pressure, my volume, my temperature. N is the quantity of the gas, and R is my proportionality gas constant. So you expect to see that equation from chemistry. And so when we articulate all of this information as the first law of thermodynamics, we're saying that if a system undergoes a change from its initial state to a final state, whatever that might be, then the change in the internal energy, the delta U, is going to be defined as the sum of the heat energy and the work. So if a system, think of a balloon, for example, of gas, if it changes in pressure and/or temperature and/or volume, it's because either heat has come in or come out of it, or work has been done on it or by it, or both. So whenever you see a change in the internal energy, it's because one or both of these things has happened. Now this equation right over here, it deserves a different color, is the key for understanding the rest of this section and the next section. And that is that when my delta U equals 0, in other words, when there is no change in internal energy, that has a name. If something is if there's no change in the internal energy and yet work and or heat are coming or going, we call this an isothermal process. Iso means the same. Thermal here, and I find this unfortunately confusing. Thermal here doesn't necessarily mean heat as much as it means temperature. And that's unfortunate, but that's the language. So we're going to have to remember isothermal is something that's taking place at a constant temperature. Now, if Q is 0, down here, if Q is 0, in other words, there is no heat coming or going into the system, and yet you still are getting a change in temperature, and work is being done either by or on your system, we call that type of system an adiabatic system. We'll have illustrations on that later. And then finally, if your internal energy is changing because heat is coming or going, and yet no work is being done, we call that an isovolumetric system, also known as an isochoric system, an older word. So these are the vocabulary words that you're going to have to get used to. So that implies then that you can have a change in a system that doesn't involve a change in temperature. You can have a change in the system that doesn't involve the change in heat. And you can have a change in the system that doesn't involve a work being done. Now, a lot of these are theoretical, or they must happen very, very fast, because as you know, any type of system that involves heat is going to easily gain or lose heat from the surroundings. So it has to happen fast so we can ignore that little bit that might be gained or lost from the surroundings. Now, another aspect of this chapter is that we're going to look at cyclical processes. Processes that go in a cycle, and you begin that cycle over again. And ostensibly, when you begin the cycle all over again, you're back to your original conditions, at least theoretically. So if you think of an internal combustion engine, you have your intake, and then where the gases, like the fuel and the oxygen, come into the system, into your piston, into the cylinder, and then they get compressed by the piston, compressing the gases in the cylinder. And then you get combustion, where a spark plug or a diesel engine, it would just be the natural increase in temperature from compression, combusts that hydrocarbon mixture and it blows up. And then you've got to exhaust the gases. And then you start that all over again, over and over and over and over. That would be a good example of a cycle. You could also talk about a bicycle pump. Push down, pull up, push down, pull up. Compress the gas, pull up. So more gas comes in, compress it again, and so forth. So just like in chemistry, the key as we go through these cyclical processes is to keep track of the system and the surroundings or environment, and recognizing that anything that's going from the system outward, in other words, if it's exiting, we give it a negative sign. If the heat is exiting the system, that's a negative Q. If the system is doing work on the environment, that's a negative W. By the same token, it's positive when the heat is coming from the surroundings or the environment into the system. That's endothermic. Or when the surroundings are doing work on the system, that's a positive W. You need to remember that. And of course, that whole nomenclature of positive negativeness, if you look at an old physics book, it'll be different. So looking at example 12.3, heating a gas. In this problem, we have an ideal gas that's absorbing. So if the gas, which is my system, is absorbing energy, the energy must be coming from the surroundings, so that's going to be a positive sign. And where our system is also going to be doing work on the environment. So that's going to be a negative sign, going outward, exiting. And so letter A, compute the change in internal energy, and letter B, if the internal energy now drops, so if your internal energy is dropping, that's going to be negative. And if something is being expelled, that is negative, going outside of the system. Keep track of those symbols, which is what I do right here. The math is simple. Keep track of the symbols. Now, this is a bit of a derivation that would not be something you would be expected to do on an AP test. But just for the record, we had this expression earlier on. We're limiting our conversation to monatomic ideal gases. Mono, of course, means one. One atom gases like helium and argon and neon. And I mentioned, I think in a previous screencast, that the 3 actually comes out of 3 dimensions. And the 2, I think, comes from the 1/2 when we were talking about kinetic energy, 1/2 mass velocity squared. We're not going to go back in the derivation. And here's where chemistry is going to be a little bit different. In chemistry, we had PV equals nRT, where N is the number of moles and R is my ideal gas constant. In physics right now, in thermodynamics, instead of talking about pressure times volume, we're talking about my change in internal energy because of a change in pressure or a change in volume. N is the number of moles, of course. Instead of R, ideal gas constant, we're going to be using this letter C for my constant. And then delta T, of course, is my change in temperature. Up here, T is your absolute actual temperature. So a change in temperature can cause our change in internal energy. Now, in these paragraphs right here, we know that if you have a monatomic gas, it can move in 3 dimensions up here. It can move in the X dimension, the Y dimension, the Z dimension. We say that it has 3 degrees of motion, 3 degrees of freedom. It can move in 3-dimensional space, 3 different directions, 3 degrees of freedom. Now, if you have a diatomic gas, not only can it move in the X direction, the Y direction, and the Z direction, but it can also, in this picture right there, it can also spin in a plane. Imagine that we're in a plane here. And these 2 particles, the red circles held together by a dash bond in the middle, they can move clockwise or counterclockwise in that 2-dimensional plane. That would be a 4th degree of freedom. And then down here, they can also move in the up and down direction, like this, rather than moving around that way. It's kind of hard to show this in a 2-dimensional surface, but they can tumble the word used in your book, in a different plane as well, and that would be a fifth degree of freedom. And when you get into a study of thermodynamics and probability and statistics at a much greater level, you talk more and more about degrees of freedom. And of course, the more degrees of freedom, the more energy a particle can hold or display. And notice that we're already up to 5 degrees of freedom, and we're talking about particles with a maximum of just 2 atoms. So the number of degrees of freedom increases exponentially as you get more and more complicated molecules in terms of the number of different ways in which they can move. So in this particular chart right here, we can see a little bit of what this molar specific heat. This is the letter C, the molar specific heat. The specific heat per mole. You had specific heat, of course, MC delta T was the specific heat for a particular kind of metal, for example. Now we're talking about the specific heat per mole, or the molar specific heat, for gases made out of 1 atom, gases made out of 2 atoms, gases made out of more than 2 atoms. And you can see that the overall amount of energy increases, generally speaking, as the molecules become more and more and more complicated. And we're going to stop there, and that gives you enough to think about as an introduction to thermodynamics.